Hello friends, welcome back to my channel. I hope you are enjoying my sessions on Wi-Fi. Please share your feedback and suggestion, and if you appreciate my efforts, then please don't forget to like, share and subscribe to my channel. So let's begin with our today's session. First of all, let's discuss the previous session quiz questions. I hope you must have chosen the correct options. Let's see. First question is, a wave is divided into degrees. How many degrees make up a complete wave? So as circle is 360 degrees, same is applicable here. So it's a 360 degree. The height or power of a wave is known as what? Amplitude. So amplitude is the strength of the signal. So the maximum the strength, the more is the height or power of a wave. A standard measurement of frequency is called what? Hertz. So 1 hertz is equal to 1 cycle. Hertz, kilohertz or mH, million hertz. So same way the basic unit is hertz. Okay, now let's start with our today's agenda. We will be discussing RF propagation and behaviors, modulation techniques and components of RF communication. So first of all, what is RF? What is RF signal or a radio frequency signal or wave propagation? What is this? The way in which the RF wave move is known as wave propagation. And when it moves, it travels through a lot of mediums, it travels through a air. There are a lot of phenomena which occur on that particular wave, which results in a diffraction, absorption, reflection. That is known as a RF behavior. So let's discuss wave propagation. Like I said, the way in which RF wave move. RF behavior, the various type of behaviors: absorption, reflection, scattering, absorption, reflection, scattering, then diffraction, loss, free space, path loss, multipath. All we discuss in today's session. So let's start with the very first absorption one. Absorption. I will show you it through a simulator. So right now this wave is moving perfectly fine. So when I pass it through, enable it to pass it through some medium. When it pass through some medium and with the medium of different density, it absorbs the amount of a quite amount of its amplitude or energy. So the result is attenuated wave. So this is called absorption. Bricks, concrete walls, water, all they absorb a signal significantly. So absorption is leading cause of attenuation. The amplitude of RF signal decreases drastically. It depends upon the medium through which it passes. So that is called absorption. Next, we will look into refraction. So bending of signal when it passes through some medium is called refraction. So if you see in the following example, so there is a light coming from and it hits the water surface. So water surface is more denser than the air. So when light passes through the water, it get reflected and deviated from its natural straight path or actual path. This process is called refraction. The process of refracting it from the original path to deviated to another path because of that. When it transferred to a different or dense medium is known as refraction. So refraction, when refraction happen, so the main major cause of these refraction is water vapor, changes in air pressure, changes in air temperature. So generally when Wi-Fi radio waves are traveling, this happens because of rain, increase in humidity. All these are the main causes of refraction in Wi-Fi radio frequencies. Next is reflection. So refraction is a bending. Reflection is they when a wave hits some object that is larger than the wave itself, then wave bounce in another direction. So when wave bounce in another direction, it starts moving into different direction, like as shown in the example. So laser, it hits the mirror, light hits the mirror and it gets reflected to in another direction, totally in another direction. So there are two major types of reflection, sky wave and other is a microwave. Sky wave occur in a frequencies less than 1 gigahertz. So it as it impact, works in a frequency less than 1 gigahertz, so it is going to impact a very it's going to impact a very little on Wi-Fi services. But microwave exists between 1 gigahertz to and 3 gigahertz, so it has a significant impact on Wi-Fi radio frequencies. So in the initial releases of 802.11 ABG, reflection is a major source of poor WLAN performance. Reflection causes a serious problems in these standards 802.abg, but in 802.11n we have a concept of MIMO. So multiple input, multiple output. We will discuss this in more in detail. But because of this advanced technology of MIMO, there it is reflection is not impacting much on 802.11n standard. But in legacy standard ABG, it has a significant impact. Also, this is reflection is the main cause of multipath and delay spread. We will discuss both of these in coming slides. But reflection it has a huge impact on Wi-Fi services. So overcoming this, there is a MU multi-user MIMO, then MIMO. So these technologies are overcoming the drawbacks of reflection. Next one is a scattering. When electromagnetic signal or a RF wave is larger than the piece of whatever medium the signal is reflecting from or passing through, multiple reflections occur. This process is called scattering. So for example, a flashlight hitting the mirror ball, then it gets scattered into a different direction at different angles. Another example, a light is hitting or a ray is hitting, RF wave is hitting a rocky terrain, it get reflected into different directions at different angles. Okay, so scattering is also, scattering also impact the your performance of the WLAN, your receiving power of the receiver. All these are going to impact the services of Wi-Fi. So any WLAN engineer who is planning to deploy Wi-Fi has to consider the all these impacts, like if there is some medium which is coming in between, if there is some rocky terrain, if there is some medium using which this phenomena will occur, scattering, refraction, reflection, absorption. So they have to be keep into the consideration all these points before designing a solution. Diffraction. So don't confuse with refraction. Diffraction is the bending and spreading of an RF signal when it encounters an obstruction. So in refraction, bending occurs when it passes through some medium. In diffraction, bending occurs because of obstruction. So this is the major difference between refraction and diffraction. So let's see an example. There is a building in between. So when transmitter transmit, because of building, the mm, it gets scattered or it gets spreaded. So this process is called diffraction. In refraction, because of medium density, the ray gets bended. That is called refraction. Free space path loss. So free space path loss is a loss which occurs, which is a a phenomena you can't stop. Whenever you transmit some wave, it it passes through a air. In air, the energy of the wave will get at the receiver end, wave will get received at with the attenuated power only. There is some loss in the energy of the wave transmitted by transmitter and the received by receiver. This loss is called free space loss. So all radio devices have a receiver sensitivity level. The radio receive a the radio can receive a wave properly only and only when the received signal is over and above the receiver sensitivity threshold. If it is below the receiver sensitivity threshold, then it the signal would not be interpreted properly and would not be demodulated correctly. So it is very much important for a W line engineer to design the solution considering free space path loss, because these are the losses which occur by default, and you can't neglect these losses. They would come by default whenever the signal transmit in a air. So take an example. There is a non-inflated balloon. This balloon has a thick walls, or you would say more power. You can't you can't pierce this balloon directly. But if this balloon gets inflated, it gets stretched, it gets spread. Same like waves get spread when it moves away from the antenna. Same way here balloon gets spread. Once it gets spread, its thickness reduces. Same way in waves, its power reduces. So free space path loss is equivalent to this analogy. So when non-inflated balloon gets inflated, its rubber gets thin instead, and before that it was a thick. So same applicable for waves. When it moves away from antenna, it gets spreaded, dispersed, and its energy get attenuated. So we discussed reflection. So multipath and delay spread. Multipath is a part of I would say result of reflection only. So how multipath will occur? So for example, you are at a home. In your home there is a dining table, there is a piano, there is a recliner chair. There are many other objects available at your home. So what happened? You are sitting at a dining table with your laptop, and your AP is placed at the top of your wall. So when first signal directly reaches to your laptop, second signal gets reflected through piano and reaches to your laptop. Third signal get reflected from your recliner and reaches to your laptop. So there are multiple signal arriving at your laptop. This is called multipath. So propagation phenomena that result in two or more paths of a signal arriving at a receiving antenna at the same time, or with the delay of some second, is called a multipath. So multipath results in four possible results of multipath are upfade. So how upfade will occur? For example, this is upward signal strength. So first signal comes, okay, and with the few nanoseconds of difference, second signal come with the very less phase shift. So phase shift, I will show you what I actually want to explain. Okay, so no material. There are two waves. Okay, now these two waves are amplituded with there is no wave difference. I will put both horizontal, oh sorry, vertical. Now so you see the amplitude is getting increased at the receiver end. So I increase the phase shift, but still amplitude is increasing because of multiple waves receiving at the receiving end. I increase further, it's still amplitude is higher. I increase up to 120, still amplitude is equivalent to the wave amplitudes. But if I increase more than 120 phase shift, then amplitude start decreasing because it has a negative impact. So up to 0 and from 0 to 120 of phase difference, If two wave reaches at the receiver, it has a positive impact or constructive multipath. They are called constructive multipath or up fade, and they result in a constructive amplitude. But if the phase difference of receiving wave is more than 120 degree, then it results in a down fade or destructive gain or destructive multipath, like as I shown here. And if the phase difference of two waves is 180 degree, then they nullify the signal. There is no signal received at the receiver end. Okay. And the fourth is, because of the difference in the reflected signal, because of the difference in time between the primary signal and the reflected signal. Okay, the difference between the time difference between the primary signal and the reflected signal is called delay spread. And because of this delay spread, there may be multiple reflected signal received at the receiver end. Because of this multiple signal receiving at the receiver end, the data get corrupted, because it is difficult for the receiver to demodulate the signal, and it will be treated as intersymbol interference. It is called as intersymbol interference. This result into data corruption. So delay spread, if the delay is very limited and it is within the phase, like as I shown it through a simulator, then it is a positive. If it is an out of phase, then it is a negative. If it is 180 degree, then it nullify. But if there is a huge delay spread, then it result into data corruption. So this is multipath and delay spread. They are directly related to the reflection. So VSWR, voltage standing wave ratio, this is very important to understand what is VSWR, and very important for designing the solution from a WLAN engineer perspective. You have one transmitter. That transmitter is connected to the external antenna through a cable. Okay. Between the transmitter and antenna, there are multiple other components like connectors, maybe amplifiers, or other components. So these components, these components would have should have same impedance. If they would not have the same impedance, then it results into a standing waves, because the incident energy, the energy forwarded by a transmitter to the antenna through cable, would get reflected because of impedance mismatch. So let's see how what actually it means. So this is a transmitter and antenna connected through a connecting cable. The impedance of transmitter and connecting cable is 50 ohm, and impedance of connecting cable and antenna between connecting cable and antenna is 80 ohm. So there is a impedance mismatch. Here it is 50 ohm, here it is 80 ohm. So what happened? So when transmitter sends incident or forward energy to the antenna, because of this impedance match, the energy get reflected. There is a some energy which get reflected. Because of this reflected energy, it will create a standing waves. This standing waves impact the performance of the WLAN. If there is no standing wave, then we would say that VSWR ratio is 1:1. The more the ratio increases, then this shows that there is a loss of energy. So I will show you. So it's a numerical relationship. It's so in simple term, VSWR is a ratio of impedance mismatch. The more the impedance mismatch, the more is the standing wave ratio, and the more is the losses. Okay. So I will show you the losses, signal loss caused by BS. So if you can see that VSWR 1:1, radiated power 100, lost power 0. 1:1 is the ideal scenario. It is not possible to achieve. So even in military, the ratio is 1:1.1. So the very less power, it's not even recognizable that there is a loss in power. But still 1:1 is not possible. In militaries, it's 1:1.1. Say, and even if it is 1.5 in real world, generally it is 1.5:1. then also it's very small amount of loss in power, which is also admissible, and it would not impact your system very much. But if further increase in VSWR ratio like 2:1, it will start increasing the power loss. So 6:1 result into 3 decibel loss in power. So it is very important that whoever be the site engineer, he must check all the equipments, interconnected equipments, that they should be of a same impedance. If there is an impedance mismatch, please get it rectified immediately, else the system would not perform part to the expectations. Attenuation or loss. So what we discussed, decrease in amplitude or signal strength while passing through some medium or while passing through air, is called attenuation. Next is amplification. Amplification is increase in amplitude or signal strength. So there are two types of amplification, passive and active. In active, you need an external power source. That power source generate extra power to amplify the signal. That is called active gain. In passive, you don't need an external power source. What happens, you need to concentrate a signal in single direction. That signal concentration or focusing result into the passive gain. So we will see EIRP in coming slides, which will help you to correlate what is passive gain. Okay, so now this we have we are done with the RF behaviors. So we are moving towards now modulation techniques. There are three major modulation techniques which are used in RF. One is ASK, amplitude shift keying. So varying the amplitude of the carrier signal to encode the data is called amplitude phase shift keying. So what happens, like you see, they decrease the amplitude to achieve the encoding. So right now, if the amplitude is higher, it is considered as 1. The half of the amplitude is considered as 0. So this is amplitude shift keying. But the problem with this ASK is that, like we see, there are a lot of uh, phenomena RF behavior which result into amplitude attenuation. So if because of any such phenomena amplitude get attenuated, then a receiver will misinterpret that signal and demodulate it wrongly. So ASK is not a advisable or recommended phase shift keying technology. Next is a frequency shift keying. So like we saw amplitude shift keying, same is frequency shift keying, varying the frequency of the signal to achieve of the carrier signal to encode the data is called frequency shift keying. By varying the frequency, so see, by increasing the frequency, they put it in as 1, and the lower frequency is considered as 0. Now a receiver should be sensitive to understand the varied range of frequencies. So single frequency receiver should be capable to understand the wide range of frequency. So this puts an additional responsibility on a receiver. If receiver is not capable to understand the wide range of frequency, then this again would considered as a corrupted signal. So FSK is again not a very much used technology. Next one is PSK. This is the most widely and recommendedly used technology or modulation technique, I would say. Phase shift key, varying the phase of the carrier signal to encode the data. So here, they change the phase to represent the data. So by in RF behavior, we have seen lot of phenomena like refraction, diffraction, but none of them is impacting directly the phase. So it guarantees the RF wave protection, data protection, and also help us to achieve multiple type of phase shifting like binary PSK, then quad PSK, QPSK, then there are furthermore which includes amplitude as well. So clubbing both these, so this technology is very much and or more frequently used in today's 802.11 technology. So PSK is most widely used one. So now next part is components of communication. So major components of RF communication are as follow. We will discuss it in two parts. First is transmitter, receiver and antenna. Other is these isotropic radiator, intentional radiator, EIRP. So first is transmitter. So transmitter is a device who takes data provided and modifies the AC signal by modulation technique to encode the data into signal. This modulated signal is now considered as carrier signal. In addition to generating a signal at specific frequency, transmitter is responsible for determining the original transmission amplitude. So original transmission amplitude, every country has its own regulatory domains. Every country has its own regulatory domains. You can't transmit a power up to some extent. I mean, you can increase the power up to some extent only. You can't increase it exponentially. So transmitter is responsible for transmitting power as well as transmitting frequency, specific frequency, at which frequency the signal get transmitted, and the amplitude of that signal. So that is responsibility of a transmitter. Okay. And next is antenna. So antenna has two functions. When antenna is connected to the transmitter, it collects the signal from transmitter and radiates the signal from the antenna in specific pattern. So that is the antenna at the transmitter end. But when it is connected at the receiver, antenna receives the signal, takes the RF waves that it receives through the air and direct these signal to the receiver. So when it is transmitted to the receiver, when it is forwarded to the receiver, receiver demodulates and decoded the signal and fetch the data from it. So there are two ways to increase the power output from antenna. One way is that generate more power from transmitter, which is as I said limited. You can't increase it up to some extent because there are regulatory domains in each country using which allows you to increase the power up to some extent. Second one is a directional gain. So directional gain is by focusing an antenna in a particular direction you can achieve the higher output. So this can be achieved by directional antennas. Now the final at the receiving end, receiver is there. So here if you can see in our example, receiver the antenna, receiving antenna is incorporated within the laptop only. It's not external and shown to you. So a receiver takes the carrier signal that is received from the antenna and translate the modulated signal into 0 and 1s. So whatever be the signal received from the receiving antenna pass it to the receiver, receiver demodulate it and translate it into 1 and 0, which is a readable form for computers for further processing. So these are the RF components fun. And now we are next is a IR, EIRP. What is the meaning of these? Let me come and explain it to you. So you have seen a motor at your home. So whenever motor runs, it produces a sound. So the sound produced by motor is a byproduct, not the intentional sound produced by or intentional waves produced by motor. Okay, so those motor is not an intentional radiator, whereas antenna or the devices that intentionally generates and emit radio frequency, like a transmitter, a device that intentionally generates and emits radio frequency energy, is called intentional radiator. Okay, power output of IR is sum of all the components like a transmitter, plus connectors plus connecting cable plus amplifier plus connecting, excluding antenna. Power of IR is include transmitter, all the components from transmitter to antenna but excluding antenna. That is called intentional radiator output of power. Then the second one is isotropic radiator. The radiator which emits in equally in all direction or omnidirectional antenna is known as isotropic radiator. These are hypothetical, and actually you would not find any antenna which equally emits in all direction. They have some directive gain in some direction. So, but it is taken as a reference for gain and all these other finding. So, for example, sun as it radiates equally in all directions, you can take sun as an analogy to understand this isotropic radiator. And the last one is EIRP. So what is EIRP? As I said, there are two ways to increase the output power of antenna. One is you increase the power, transmitter power, and you can increase the amplification, but that you can't increase exponentially. There is a limit or transmit power guidelines for each country, so you have to be comply to these transmit power only. Now the other way is that you have an input power of 1 milliwatt. Using a directional antenna or focus or concentrated antenna, you radiated power of 4 milliwatt. So this increase in power is called EIRP. So here you can see transmitter connecting to directional antenna through connecting cable, power generating a power of 1 milliwatt, but power coming out from directional antenna is 4 milliwatt. The so EIRP is the highest signal strength that is transmitted from a particular antenna. So maximum power strength. So using a directional antenna, the actual power has been increased. So that is called EIRP. So friend, we are done with today's session. We are done with today's session, and I hope these are the basic thing which you have already, I mean, done in your school during your schooling time, or you may have done it in your during your college time. But these are very important concept from examination point of view, as well as from your understanding of RF, and for further lessons which we are going to do in coming videos. So this is very important, so please clear all your concept with respect to these RF behavior components, because these are going to be repeat again and again in each of our video. So so friends, now it's a quiz time. Which of the following statements are true about amplification? So I'm holding some time on for on this screen so that you can just have a look at the options. When an RF signal bend around an object, this propagation behavior is known as what? When the multiple RF signal arrive at a receiver at the same time and are with the primary wave, the result can be of the primary signal. What are some objects or material that are common causes of reflection? So friends, I'm done with today's session. I will come back soon with the new video. Please do subscribe to our channel, okay, and keep posting me your feedback and suggestions so that I can improve my uh, videos further. Thank you. Thanks a lot.